Welcome to the training session on the GOES-R Rainfall Rate Baseline product. Bob Kuligowski is the developer of this product. I'm Dan Bicus and will narrate the training. For our learning objectives, we're going to briefly describe the GOES-R Rainfall Rate algorithm. We're going to describe strengths and limitations of the GOES-R Rainfall Rate algorithm, and we'll analyze example imagery of the GOES-R Rainfall Rate product in AWIPS. Estimates of instantaneous rainfall rate are output every 15 minutes at full ABI-IR pixel resolution with a latency of less than 5 minutes and are available over the full disk day and night since IR bands are utilized. Rainfall rates up to 3.9 inches per hour can be output by the algorithm. The motivation for this product can be easily understood by first understanding the differences between satellite-based rain rates derived from a microwave instrument versus that from an infrared instrument. Microwave-based rain rates are generally more accurate than IR, but less timely since they're on polar orbiting satellites. Meanwhile, IR-based rain rates are generally less accurate than microwave, but more timely than microwave since they are available from geostationary satellites. The solution is to use the more accurate microwave-based rain rates to calibrate an IR algorithm and thus optimize the accuracy, frequency, and timeliness of the product. The GOES-R Rainfall Rate product makes use of GOES-R ABI bands and is calibrated against the CPC combined microwave field known as MW-COM. The ABI bands used as input are bands 8, 10, 11, 14, and 15. These bands contain information about the cloud phase and particle size and help to discriminate. The algorithm derives rainfall rate in 2 steps. First, identify pixels that are experiencing rainfall using a matched data set of ABI, IR, and microwave rain rate data. Use discriminant analysis to determine which ABI, IR bands are most skillful at discriminating between raining and non-raining microwave pixels and the required threshold values. And then the second step is retrieve rainfall rates where rainfall has been detected. This is using a matched data set that contains only raining microwave pixels. It uses a stepwise forward linear regression to determine which ABI-IR bands, or band differences, have the strongest relationship with microwave rain rates. To account for nonlinear relationships, each ABI-IR band is also regressed against the microwave rain rates in log-log space to form a supplemental set of predictors. The distribution of rainfall rates are then adjusted via a lookup table to match the distribution of the microwave rain rates. Note that this calibration was done offline and is fixed in the initial version of the product. A future version will allow the calibration to be updated in real time using recent ABI, IR, and microwave rain rate data. Several assumptions are made when estimating rain rate from IR data. One is that the cloud top temperature is related to cloud top height. Another is that the cloud top height is related to the strength of the updraft transporting moisture into the cloud, and further, that updraft strength is related to rainfall rate. Generally speaking, colder clouds are associated with heavier rain, and warmer clouds are associated with light or no rain. The performance of the rain rate algorithm is improved when the data are divided into 3 cloud type categories based on thresholds between the various band brightness temperatures given here. They are called water, ice, and cold top convective clouds, but these are not exact classifications. The purpose is to separate clouds with different relationships between the IR brightness temperatures and the rain rates. Separate calibrations are also applied over 4 geographic regions over 30-degree latitude increments, which yields 12 distinct rainfall classes in the algorithm. When using satellite QPE, it is critical to remember that while our primary interest is in rainfall rates at ground level, satellites detect cloud top or cloud level characteristics. One of the differences between the two can be in location. In sheared environments, rain rate shafts are not vertical, so the surface rainfall can be displaced by up to a few pixels from the locations indicated by the IR imagery. Also, satellites cannot directly observe orographic effects, subcloud evaporation of hydrometeors, and subcloud phase changes. Some of these issues can be addressed with the help of NWP model data. Examples include using relative humidity fields to reduce rain rates in arid regions, or using wind fields to attempt to adjust for orographic enhancement. Now we'll review strengths and weaknesses of the product. Satellite rain rate estimates are best for deep convective rain. Satellite rain rate estimates perform poorly for stratiform precipitation. Weaknesses of IR retrievals include underestimating or missing shallow stratiform clouds that are near or warmer than 0 degrees Celsius, which can include orographic clouds or very shallow convective clouds, such as trade wind showers. Also, cirrus associated with convection can be incorrectly identified as rainfall regions, even with the help of additional spectral bands. This is an example of the GOES-R rainfall rate baseline product as displayed in AWIPS for Hurricane Michael. Units are in inches per hour. Note the overall decrease in rainfall rate after the hurricane makes landfall. For this animation of Hurricane Michael, we'll make use of the tracking meteogram tool for a circle over the Gulf of Mexico in the path of the hurricane. The first thing you probably notice is that rainfall rate values exceed those that are shown on the color bar. Recall that the maximum values the product is designed for is 100 millimeters per hour, which is about 3.9 inches per hour. We see this upper limit in the tracking meteogram tool on the right, and you also see these values in the AWIPS cursor readout. The color bar saturates a white color for any values above 3.0 inches per hour or greater. Think about how you could make use of the tracking meteogram tool to assess rainfall rates heading towards your region of interest. Although, keep in mind that biases will vary from case to case, and generally speaking, convective rainfall rate estimates are more accurate than stratiform rainfall rate estimates. Here's the GOES-R rainfall rate animation for Hurricane Florence. Note that the aerial coverage of the highest rainfall rates are not as high as Hurricane Michael. Instead, we see bursts in higher rainfall rates. Recall that unlike Michael, storm motion slowed down considerably as it approached land, leading to significant flooding in the Carolinas. Consider what else you might analyze along with the GOES rainfall rate product. Here's a 4-panel example from AWIPS to provide some possible ideas. Certainly the IR band at 10.3 microns, as shown in the lower left, is a good idea since the trends in IR brightness temperatures will help you interpret trends in the GOES rainfall rate product. Other options could be one of the water vapor bands, as the mid-level water vapor band at 7.0 microns is shown in the upper right, which can provide details of the environment around the storm. Perhaps monitoring for mid-level drying is a concern. If so, you might want to consider the 700 to 500 millibar precipitable water from the advected layer precipitable water product, as shown in the lower right panel. Noise as a result of instrument warming due to the loop heat pipe issue on GOES 17 significantly degrades the accuracy of the GOES rainfall rate product. The GOES rainfall rate product from GOES 17 data will not be usable for at least several hours a day within 6 weeks or so of each equinox when the sun shines directly on the instrument. Mitigation work is ongoing to determine how long the data are not usable. Keep in mind that GOES 16 is not affected by this issue. It's important to keep in mind that the baseline product utilizes the algorithm version from September 2010. Known limitations of this version include it does not update its calibration in real time, which will degrade its accuracy somewhat, occasional inconsistencies in rain rates between types, and a symptom of this could be holes in deep convective clouds. Also, it does not account for subcloud evaporation of rainfall. It tends to overestimate rainfall in relatively dry environments. A future release will address these limitations. In summary, the current operational NESDIS algorithm, the hydroestimator, uses one band, the 10.7 micron band, with 2 cloud types. It will be replaced with this multi-channel product, the GOES-R ABI bands with a fixed calibration from a climatological microwave retrieved dataset as input, and 5 ABI bands that allow various band differences for discrimination between cirrus and overshooting cumulonimbus, and also account for cloud phase and thickness. Satellite rainfall estimates are informative, but must be understood to make the best use of them.